We've all seen it, right? In movies, on a hospital monitor, that jagged, rhythmic line, beeping away. It's the EKG. But what is that squiggly line actually telling us? Well, today, we're going to crack the code. It might look like just a random pattern, but it is anything but. It's a language, a detailed story written by your heart, spark by spark, beat by beat. And by the end of this, you and we're going to learn the basics of that language together. So, where do we even start? Well, like with any language, you gotta know its history, right? Its origins. In the story of the EKG, it actually starts somewhere kind of weird. Not with a heart, but with a frog. Yeah, really. It all kicked off way back in 1790 when a guy named Luigi Galvani wowed an audience when he made a dead frog's legs literally dance with a jolt of electricity. This was huge. It proved a link between electricity and living tissue. Fast forward about 65 years, and scientists confirmed that the heart basically runs on its own electrical pulses. But the real game changer came in 1901 with Willem Einthoven. He invented a machine that could actually record these pulses right from the skin and gave the waves their now famous and, let's be honest, kind of random-sounding names: P, QRS, and T. Okay, so here's the absolute key takeaway. An EKG, or electrocardiogram, isn't just a picture of a heartbeat. No. It's a recording of the electrical events that cause the heartbeat. It's a direct look at the spark that tells the muscle to squeeze. So where does this electricity even come from? It's not like the heart is plugged into a wall outlet, right? Nope. The power source is microscopic. It's found inside every single heart muscle cell. Okay, so think about a heart muscle cell. It's called a myocyte, as a tiny, tiny rechargeable battery. When it's just resting, chilling out, its interior is negatively charged. It's polarized, but when it gets the signal to beat, all these channels open up. Positive ions rush in, and the inside of the cell flips to a positive charge. And that electrical flip, that's called depolarization. It's the spark that makes the cell contract, that makes it squeeze. And here's the cool part. This doesn't just happen in one cell at a time. Depolarization spreads from one cell to the next, kind of like a wave or the domino effect. It's a cascade of positive charge that sweeps across the heart muscle, getting everything to squeeze in perfect time. Okay, so after the big squeeze, what happens? The cells have to reset, right? They can't stay fired up forever. That process is called repolarization. Basically, they pump those positive ions back out, returning to that negative resting state, getting all charged up and ready for the very next beat. All right, so we've got this electrical wave, depolarization and repolarization. Einthoven's big idea, his stroke of genius, was building a machine that could draw a picture of that wave. So how do those tiny little cellular events create that famous PQRST shape we see on the monitor? Okay, let's walk through the entire story of a single heartbeat. Step 1. We start with the P wave. That small bump, that's the heart's natural pacemaker firing off and causing the top chambers, the atria, to squeeze. Step 2. Then, you see that flat line? That's not a mistake. It's a pause, and it's super important. The signal deliberately slows down to give the bottom chambers, the ventricles, time to fill up with blood. Step 3. Now, for the main event. That giant spike? That's the QRS complex. This is the electrical signal blasting through the powerful ventricles, causing that massive contraction that pumps blood out to the whole body. And finally, step 4. The T wave. This is just the ventricles resetting, repolarizing, getting ready to do the whole thing all over again. So just think. Atria squeeze, pause to fill, ventricle squeeze, reset. That's the whole cycle. All right, so we know the alphabet now. P, Q, R, S, and T. So let's start reading some words. I'm going to show you a really simple, practical skill you can use just by looking at an EKG strip. No kidding. So take a look at this. Now that you know the parts, can you figure out how fast this heart is beating? You might think you need a calculator or some crazy math formula, but you really don't. All you need to know is how to count. Okay, check this out. This is a super clever trick to figure out the heart rate just by looking. First, find one of those big spikes, an R wave, that lands right on a heavy dark line. Got it? That's your starting point. Now, you just count off the next heavy lines using this magic sequence. 300, 150, 100, then 75, 60, 50. Wherever that next R wave lands,
that's pretty much your heart rate. So if it lands here, on the third line after your start, boom, the rate is about 100. See? No calculator needed.
And this idea isn't just some party trick. It's captured perfectly by Dr. Dale Dubin, who wrote a classic book on EKGs. He literally said, observation alone will do it. The EKG is meant to be read visually. It tells its story at a glance, as long as you speak the language. Wow. Okay, so let's just recap for a second. We've gone from a twitching frog's leg to the tiny batteries inside our heart cells to decoding the waves, and we even learned how to calculate the heart rate. So let's zoom back out and just remember why this simple little test is so incredibly powerful. What's the big deal? Well, it means that with just a few sticky pads on the skin, we get this profound look inside the human body. The EKG is totally painless, it's quick, it tells us the heart's rate, its rhythm, is it steady or is it all over the place? And it gives us these incredible clues about the health of the heart muscle itself. It is, no joke, one of the most important diagnostic tools in all of medicine. So, in the end, that simple, jagged line on the screen, it's just a translation. It takes a microscopic electrical spark and turns it into this powerful, epic story about our health, our vitality, really the very rhythm of our life. So there you have it. We've just cracked the basic code of the EKG. And it kind of makes you wonder, doesn't it? What other secret languages, what other hidden codes is the human body using to talk to us, just hiding there in plain sight, waiting for us to figure out how to listen?